Hello, friends. It's your boy, Mr. Stone, and today we're going to be talking about electromagnetic induction, which is how electric guitars work. You see, in an electric guitar, you have pickups that work by the principles we've been talking about, the relationship between electricity and magnetism as they interact with each other, and in fact create each other. Hans Ørsted discovered that electric currents make magnetic fields, but later, Michael Faraday discovered that a changing magnetic field generates an electric current. So, how do these work? When you plug a guitar in, you get a steady current from the amplifier through the guitar back to the amplifier. That current goes through these, which are called pickups. Why? Because they pick up what the string is doing in order to tell what sound it should be producing. But what does that have to do with magnets? Well, I can show you. Alright, so in the guitar there is a solenoid wrapped around a permanent magnet. One permanent magnet for each of our strings. So that solenoid has a current going through it, and if you have no string movement whatsoever, then you should have no variance in the current. But those permanent magnets magnetize the string above it. So the magnetic field goes from the pickups into the string and back. So if you move the string, it causes the magnetic field to kind of have to move back and forth along with it. A changing magnetic field will generate a current in the solenoid wrapped around it. So since that solenoid already has a current in it, that magnetic field's oscillating because the string oscillates, the string vibrates, the magnetic field vibrates, which means that the current it makes kind of goes back and forth, adding and subtracting from the signal coming from the amp. So what you send back to the amp has variances in it that tell it how the string is moving. Thus, Faraday's discovery allows for rock and roll. This also is how one of these works. Instead of using strings to move a magnetic field, what you do is you have a membrane. The membrane or diaphragm of the microphone is the part that when you talk, the air you push is caught by that and it causes it to vibrate. Vibrates to the frequency in your voice. Attached to that membrane is a permanent magnet. And as that permanent magnet shakes back and forth inside of a solenoid it's wrapped around, just like the guitar pickup, you'll get variances in a current, and that gets sent to a speaker. Now, the speaker works exactly like we've been talking about. You vary a magnetic, if you vary a current through a solenoid, it causes a varying magnetic field, like turning an electromagnet on and off a lot. Well, that shakes a permanent magnet that's nearby to the solenoid, that's attached to a diaphragm, kind of like a microphone, but backwards. And in fact, that is a running theme for our lesson this week. If it works with electricity and magnetism, you should be able to run it backwards. If it is used to make electricity using a magnet, run it backwards, put electricity in, and it'll give you magnetic work. If you put magnetism work in, it'll give you electrical current back. So a generator can become a motor. A motor can become a generator. A speaker can become a microphone. In fact, you can take your headphones, plug them into the microphone slot on your computer or any other recording device, and if you yell into them, it should work. I've had friends who recorded entire EPs yelling into their headphones because they couldn't afford microphones back in college. So for electromagnetic induction, what you need to know is, as I was saying, Hans Ørsted discovers that a current yields a magnetic field. But Faraday found that it's also kind of reversible. Michael Faraday discovered that if you have a change, delta, meaning change, in our magnetic field, that will yield a current. So if you had, for example, a solenoid and you take a bar magnet and plunge it into the solenoid and pull it back out, that magnetic field moves. Movement is a change. Moving that magnet in and out of that solenoid will generate a current in the solenoid. So you can cause a light bulb that's attached to that to get a current through it. Here, I'll show you. Here are some Christmas lights that are attached to a generator I'm holding right now. There we go. So the Christmas lights are attached to the generator. Within this generator, there is a motor. A motor has a permanent magnet attached to a stem. I can turn that stem with this crank. Therefore, I'm going to spin the magnet inside of the motor. And then wrapped around that is a solenoid. The two ends on either end of it go to the lights. So if I move this magnet, according to Michael Faraday, I should get a current in the solenoid, and I can send that to these light bulbs. Let's see. Oh, barely there, but did you see it turn on here? Look closely at the blue bulb. It turns on. I get a current from moving this magnet inside of the motor. But as soon as I stop, the current goes away. If I move the current, or excuse me, if I use the crank in the opposite direction, I'll actually get oppositely directed current. Now, the incredible thing is that this is reversible. So here, this is a battery. This will supply a current. When I attach that here, my generator turns into a motor. Supplying a current through the solenoid causes the magnetic field to change, moving my magnet around in a circle. All of this electromagnetic induction stuff works both ways. So what's the go of this? Well, Faraday observed that the faster the rate of change in the magnetic field, the greater the induced current. So how does this work? Take a solenoid like this. And then a bar magnet. Here's our north, here's our south. Plunge the bar magnet through that, pull it back out over and over. The faster you do it, the greater the induced current will be. So the faster this magnet moves on the inside of the solenoid, the greater the induced current coming out of the ends of the solenoid will be. This is how you get electricity generated in almost all modern generators, except for solar panels. If you can think of a power plant, it works by this principle. Tico, where your parents and I both buy our power, Well, Tico has these plants that burn coal. The burnt coal generates heat. Heat boils water. Boiling water has steam that rises and it pushes a turbine. That turbine begins to spin and it causes a permanent magnet inside of a gigantic solenoid to turn, just like my generator here, but bigger and steam powered. That produces the current that gets all the way from Tico to you. Or you could skip out on the coal and turn that a different way. For example, if the inside of the earth is hot where you are, that's called geothermal power. So you pump water underground where it's hot because you're near some volcanic fault or something. Pump the water underground, gets hot, it boils up, push that over a turbine, turbine spins a magnet, induces a current. Or why do you need water to be the gas that's moving? We've got gas moving around all the time. If it's windy, just have the wind blow a turbine. Wind power turns the magnet inside of the gigantic solenoid. Are you noticing a pattern here? All electric generators that work on a magnet into a current are working by this principle that Faraday discovered. In fact, let's write that out. Generators Now notice that I phrased this in terms of work and energy. Remember that work done is energy put into something. So when you do the work on a magnet, that turns into the electric energy that pushes the charges to flow. And that's how you get a current. So whereas this talks about the field and the current, this talks about the work done to change the field to give you the energy to start moving the current. As we saw with the generator I was playing with, and as I spoke about with the microphone and a speaker basically being the same thing but run backwards, you can take a generator, plug it up to an identical device, and where the current is generated in one, the current flows to the solenoid of the other and does work on the magnet on the other end. That is what we call a motor. A motor is a device that turns into work done on a magnet. All right, guys, if you have some stuff laying around at home, here's how you can apply some of what we're doing this week in order to build your very own custom speaker out of using only some styrofoam cups, a little bit of wire, and a magnet that you've pulled off of your refrigerator. 2 styrofoam cups is your starting point. One will act as the diaphragm of your speaker, the other one will just be a cover. You'll need a magnet. If it's circular like this one, then you glue it onto the back and you'll stick your solenoid in the hole in the middle of the magnet. If you just have a flat refrigerator magnet or neodymium magnets, then you would put those inside of the cup and skip the part where you cut out the hole in the back. Either way, once that magnet is secured either to the inside or outside of the cup, grab some wire. Remember that the number of solenoid windings determines the strength of its magnetic field. So you're going to want at least 60 turns. The closer you can get to 100 turns of the wire around whatever it is you wrap it around, the more powerful your magnet's going to be. The 2 loose ends of the wire are your electrical leads. We'll put a current through it by having a positive terminal attached to one side and a negative terminal attached to the other. Affix that to the cup on the opposite side of the magnet. You'll take a headphone plug, strip the wire back a little bit. The red side goes to one side of your solenoid. The black wire goes to the other side of your solenoid. Tape them off so that the exposed wires do not touch. Otherwise, you just have a short circuit. If you're in a hurry, this whole step with the second cup could be skipped, but it's nice because it allows a cover to keep everything from touching. And boom, you've got your own homemade speaker. Another important application of the principles that we're talking about this week is based on an extension of what we're doing right now called Lenz's law. That is Lenz with a Z. Lenz's law states that an induced current, that is a current that you make by having a changing magnetic field near a loop of wire, always flows in a direction that opposes the change that induced it. That one sounds really weird, but I can show it to you with an example. You can take a magnet and a copper pipe, and you can see this for yourself with the magnetic braking. Here's a copper pipe. As we all know, copper is not iron, nickel, or cobalt. So, despite being a really good conductor, it's not magnetic. Or at least, it shouldn't be. Here's a neodymium magnet, a powerful little magnet, and it is not attracted to the copper pipe. As you can see, does not stick. However, when you drop it down the magnet, instead of a good G of acceleration, it falls really, really slowly. This magnetic braking is an example of Lenz's law. Because the magnet is falling, its magnetic field falls with it. A moving magnetic field induces a current. Copper is a great conductor, so the current moving through the copper opposes the motion of the magnet that creates and induces that current. Lenz's law. For further work with Lenz's law, let me show you something here. This uses electromagnetic induction for kind of a fun example. Here I've got a piece of copper. Copper is not iron, nickel, or cobalt. And as you notice, here is a reasonably strong little magnet, has no effect on the copper, nor does it have any effect on these aluminum rings over here. This device, as you can see here, has a solenoid. You can see the copper wire is wound into a solenoid, and when I flip the switch, it puts an alternating current, an on-off, on-off, on-off current into this solenoid. So we'll get a changing magnetic field. Faraday told us that where you have a changing magnetic field, you can induce current in nearby stuff. So this is not normally magnetic. It's not magnetizable, but it's copper, and everyone knows that copper can be used for wires. Hell, it's used for wire right here. But copper is a fantastic conductor, even if it's a terrible magnet. So when you put it on here, even though this magnet does nothing to it, this changing magnet will do something to it. Pretty neat, right? Here's how it works. This oscillating current going back and forth, alternating, gives us an oscillating magnetic field. That induces a current in the copper piece. Because there's a current in the copper piece, currents are magnetic. But Lenz's law tells us that it'll be in the opposite direction of the change that created it. Thus, it gets pushed away and launches up. It even works with the aluminum. Aluminum, also not magnetic. But there you go. Now here is a surprising one. Here's a piece of aluminum. This is larger than the other piece of aluminum you just saw launch. Which one do you think will launch up higher? The big one or the small one? Well, typically you'd think of Newton's second law. More mass requires more force to accelerate. So you might be thinking that the small guy should launch up higher. Let's see. Bigger one. Is that surprising to you? Why do you think that is? It says more surface area. There's more stuff in here to have a current going through it. With more current going through it, you get a better magnet to push against. And in fact, if you have these connected so that a current can go through them, watch this. Woo! Even more current gives you even more magnetism to push against. Lenz's law. Now, one last thing before I put this away, because this is really fun. Inside of my solenoid, I've got nothing but air. Air doesn't become magnetized. It just doesn't happen unless you turn it into a plasma. So, as you can see here, my magnet sticks to this bar. This is a bar of iron. Iron is magnetizable. So, if I put the iron in here, it's going to fall into the domain that lines up with this oscillating magnetic field here. In other words, it'll give me more stuff for this magnet. More magnetic power when you have more stuff in the domain. So consider, here's the piece of copper with air inside of the solenoid. I replace that air with iron, and we should get some more power. Right? Let's do that one again. Fun stuff. But Lenz's law totally explains it, just like it explains magnetic brakes on a roller coaster. Well, it explains why we can have fun with our ring launcher. Now, one final note is that, man, I've launched this thing a few times now, and it's hot. Why do you think it's hot? Well, I had a current going through it. This has some resistance, and resistance turns electrical energy into heat. So that's another further bit of proof that what's going on here is what I say it is. Also, I've seen variations of this with Christmas lights down the piece of copper, and when you flip this on and it begins to shoot up, you see the lights light up. Interesting stuff. Another example with my hand crank generator I was using earlier, the faster I rotate it so I get more current, it actually becomes more and more difficult. I have to apply more and more force because it begins to fight back because there's some magnetic braking due to Lenz's law. And one last piece of information to share with you for this week is that electromagnetic induction is how transformers work. Transformers, I do not mean cars that turn into robots, but rather those big black boxes that you have to plug stuff into in order to plug it into the wall. This is a typical wall wart USB transformer. As we know from our previous unit, the wall provides either 120 or 110 volts, but USB is only ever 5 volts. So how do you get that 120 from the wall to step down and become only 5? Well, you use one of these. You guys have lots and lots of these USB transformers. The way it works is a current from the wall goes into a solenoid, and that solenoid makes a magnetic field. That magnetic field affects a neighboring solenoid, but the neighboring solenoid will have fewer wire loops. Since this one has fewer wire loops, you will get a lower current, as though there was a lower voltage induced over here. So 120 volts in, you can get 5 volts out. Or here is a step-down transformer with less difference in the windings. Input is 120, the output is 12 volts. So this drops it down 10 times, meaning there's 1/10 as many windings in the less wound loop, which is also kind of interesting because if you plugged into this thing backwards and you put 12 volts in and attached like alligator prongs to these terminals here, 12 volts in, you'd get 120 volts out of it. Transformer works both ways, just like all of these devices we've explored today work both ways. You want a motor to spin backwards? Plug it up backwards. Have the current go the other direction so the magnetic field flips. You want a motor to charge your phone? Well, just turn it, and instead of using electricity, it'll induce an electrical current. Amazing stuff, and incredibly useful. Now that you kind of know what to look for in the world around you, you will see the consequences of Faraday's discovery that a changing magnetic field gives you a current and vice versa. You will see that everywhere. Everything that you plug up to a battery and it spins, Faraday. Everything where you have a current coming out of your wall because you're buying it from Tico, they're generators based on the work of Michael Faraday. It's everywhere. And that's the wonderful thing about physics, is that it's everywhere, whether you know to look for it or not. But once you know to look for it, you can appreciate it, you can control it, you can contribute to it. Adios, kids.